Let's take a look at the idea of transformations of sine and cosine. The basic sine and cosine functions involve oscillations between +1 and -1. As x increases, the sine function starts at 0, goes up and down and up and down. And similarly, cosine starts at 1 and goes down and up and down and up. And so these functions can be used to represent kind of repetitive behavior, oscillating behavior. If you think about like a string, a musical instrument, maybe if you pluck a guitar string, it goes back and forth. And the wave sort of motion of that string can be represented by sine or cosine functions. And so, these are useful in describing that, but in some situations we want to describe them in a slightly different way. So, the characteristics of these functions involve an amplitude that equals 1, because the difference between the highest point and the lowest point, if I take that maximum minus the minimum and divide by 2, I get +1 minus -1 divided by 2 is 1. The period, well, the normal period for these functions is 2 pi, because it takes 2 pi units in terms of radians to get from one sort of highest peak to the other, or from 0 and then back to the similar 0 at 2 pi. But for other situations, we might want to speed up that period or slow it down. These properties, they're interesting as they are, but we might want to transform them in order to fit other situations. And so the basic transformations that we're going to talk about in this video are linear transformations, where we might multiply the sine function by some number on the outside, a, or we might multiply x on the inside by b. We could also subtract a number on the inside, or we could add something overall to the outside. We could add d to the outside. In a similar way, I could take y equals a times cosine of bx minus c plus d. So that's a d. So these transformations are essentially similar for both sine and cosine. So let's just take a look maybe at the sine function and see how the sine function changes for those different types of transformations related to the numbers a, b, c, and d. So let's consider just what happens if we introduce d in our formula. So I have something like y equals sine of x plus d. So if d equals, say, -2, I get sine of x minus 2. And to see what that looks like, we can graph on a graphing calculator. We can graph sine of x along with sine of x minus 2. It's convenient to use the trig option, option 7, and if I just type the number 7, it'll take me to that setting. And so there's the regular sine function, and there we started graphing the second function, the sine function minus 2. And so we can see what's happening is that for every value of that second function, the graph is 2 units below where it used to be. So rather than crossing through 0 at 0, the graph is now down at -2. So d introduces a vertical shift. If d is positive, it's going to shift the graph upward. If d is negative, it's going to shift it downward. Well, let's think about what happens if we just introduce a into our picture. So if I have y equals some value a times sine of x. So we could choose a particular value. Let's say we want to take -3. So in a similar way, I want to compare the graph of sine of x and -3 times sine of x. So if I go to the trig window again, regraph that, I see the original sine function, and then here's our new sine function. And a couple things become apparent. Because there's a negative sign in front, whenever the original sine function was positive above the x-axis, whenever the y values were positive, they're now negative. Wherever they were negative, they're now positive. Because there's a 3, when the graph used to reach +1, now it reaches -3. When it used to reach -1, now it reaches +3. So this also, the value for a, also affects kind of a vertical change on the graph. It stretches it vertically, and because a is negative, it also causes a reflection across the x-axis. So one of the characteristics that we've talked about has definitely changed here. The maximum is now at 3, and the minimum is at -3. And so that causes the amplitude to change. In this new picture, the amplitude is 3 minus -3 divided by 2. But that's 6 divided by 2, that's equal to 3. And so it turns out in general the amplitude of a transform function is always going to be the absolute value of a. So let's consider what happens if we just replace b. So I might have something like y equals sine of b times x. Or in particular, we might have something like y equals sine of 2x. This is a change that happens inside the function, and so it's going to differ from what we've seen with a and d because it's going to affect things horizontally. This change affects the x values before the function is applied. So let's take a look at the graph of what this new function will look like. And again, we can compare sine of x to sine of 2x. So there's sine of x, the normal sine function. If we look at sine of 2x, what's happening, if you think about what's happening here, the 2 is speeding things up. So in particular, what used to happen at pi is now happening at pi over 2. So the 0 that in the original function happens at pi now happens at pi over 2, because if I plug in pi over 2, multiplying by 2 gives me pi, and so the value at pi over 2 is 0. In a similar way, the value at pi over 4 in this new function, the value of pi over 4 is going to be what used to happen at pi over 2. So the peak used to be at pi over 2, now it's at pi over 4. It might be helpful to just look at the graph of the sine of 2x function. So let me turn off sine of x. And if we look at just the graph of sine over 2x, we see that from -2 pi to 2 pi, we actually go through 4 cycles instead of just 2. That means that this sort of transformation, it affects the period of the graph. So in general, the period is 2 pi. If I introduce a value b like this, it's going to shorten the period. It's going to speed up how quickly we go through a cycle. And so the period, a formula for the period is 2 pi divided by b. So in this example, the period here is simply pi. 2 pi divided by 2. If the value for b is negative, it causes a reflection across the y-axis, but we assume the period to be a positive amount, and so we take the absolute value of that. If we consider what happens if we just introduce a value c, we get a graph that has a function that has a form y equals sine of x minus c. So this is the generic form with a minus sign in front of c. So an example of that, let's say we take x minus 1. So if we look at a graph of these two, this is the original sine function, and then sine of x minus 1. What we see, again, because the change here is inside the function, we see a horizontal change. What used to happen at 0 now happens at x equals 1, because if I plug 1 in here, 1 minus 1 is 0. And so this is a shift to the right, and we call this the phase shift in this situation. So the phase shift is determined by c. The phase shift is 0 if there's no value in this situation. If there's no number added or subtracted inside the function, the phase shift would be 0. But it also is affected by b. So the phase shift is actually given by c divided by b. Because if we introduce a value of b, if we change the period, it affects the phase shift. It makes the phase shift either shorter or longer. And we can see that if we introduce that value. Let's say we take a look at sine of 2x. So we saw a moment ago, this is the basic sine function. We saw a moment ago that the graph was shifted 1 unit to the right, so this 0 happened at 1. Now the 0 is actually happening at 1/2. And so if I can see that if I trace along the graph and enter in 0.5, that value is giving me 0, where in the earlier graph that would have happened when x equals 1. So the phase shift, it depends on both c and b. So the graph that we've just seen was y equals sine of 2x minus 1, and the phase shift was 1/2. And we can think of that, another way to kind of think about that, we could factor out a 2 on the inside, and this would become 2 minus 1/2. And so the 1/2 kind of relates to that sort of factored form of the inside of the sine function, of the argument of the sine function. So the phase shift here would be just 1. So let's take a look at a summary of the formulas that we've seen.